Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back to another exciting session, and we are talking about bonding and the periodic table. Okay, so I hope you are ready. This week we are covering the periodic table, groups, periods, as well as properties of metals and non-metals and metalloids. Okay, so let's just get right into it. This is the learning objective. We are learning about valence electrons. What are valence electrons? Compounds, reactivity, ductile, malleable, luster, semiconductor. All of these words, we'll learn what these words mean. Let's begin with this. Bonding and the periodic table. So what are we talking about here? We're talking about why different elements bond together. That means why do they form compounds? Why do they join each other? And turns out the reason, simply put, is down to one word, and that is electrons. Okay, but we'll get into that shortly. Now some of you might be familiar with this over here. This is the Hindenburg disaster that happened back in 1937. It was a huge airship, and this was in Germany, and they made a mistake. They filled the Hindenburg with hydrogen gas. Now, what is wrong with hydrogen gas? Nothing, actually. Hydrogen gas is it's excellent. It's fantastic. It's useful. We want hydrogen gas. We need it. So what was wrong with filling the Hindenburg with hydrogen gas, you might ask? Well, turns out hydrogen gas, even though it's very light, it's also rather explosive. So here's hydrogen. Here's my periodic table, and hydrogen is right here. So it's actually part of group 1 elements. But it's a bit of a special case. It's not really a metal. It's a non-metal, but it's part of group 1. But hydrogen is explosive. Can you guess what happened? They filled the Hindenburg with hydrogen and it exploded. We've got some questions here we should answer. How did it explode? Somebody might ask. Well, there's a couple of theories, but one of them is that there was static electricity, and there was a charge of static electricity that jumped from the tower. Oops. Oh, these are a bit tricky today. Come on. Here we go. So it was a charge of static electricity that jumped from the tower here to the Hindenburg as it was passing by, and it caused an explosion. That's the theory anyway. Right. So we've got some questions we can answer now, and the questions are as follows. Use the periodic table to predict why krypton under noble gases is not used in the airship. Let's have a look. So this is hydrogen, it's over here, it's number 1, and this is krypton, it's over here, and it's way down. It's number 80. Well, it's number 36. It's got an atomic mass of 84, but it's got an atomic number of 36. It's a noble gas, which would have been okay because we know it's not reactive. However, it's heavy. Okay, it's got krypton. Oh, come on. Krypton has a high atomic mass. What does that mean? It means it would have never taken off. This airship would have been a ground ship. Krypton is heavy. Yeah, so not all gases have the same mass, just like not all solids have the same mass. So it would have just stayed on the ground. Krypton was just far too heavy. Even though it was stable compared to hydrogen, it is just far too heavy. How would the results of the spark have been different if the Hindenburg had been filled with helium? Now, helium, on the other hand, is quite light. Where is helium on the periodic table? Helium is in group 2, and it's number 4. Here we go. It's got an atomic mass of 4. It's number 2. It's got an atomic mass of 4. And it's in group 8 or 18. So helium would have been ideal. Why didn't they use helium? Too expensive. Right, so I mean they just needed a whole lot of helium, didn't they? So helium would have been fantastic because you actually can fill helium balloons with helium. However, the calculations would have been slightly different because helium is heavier than hydrogen, 4 times heavier than hydrogen, even though it's still quite light. However, helium would have been the ideal gas because it's not reactive. It's not like hydrogen. It doesn't explode. It's very stable. All of the noble gases are stable. All of these guys are very stable because they've got a full outer shell. They don't need any electrons from anyone, and they don't need to donate any electrons to anyone. So these ones here are very stable. These ones here are very reactive. These are reactive nonmetals. These are the most reactive metals. Now, why is that? Because these ones have one electron to get rid of. These ones need one electron to be stable. So these ones and these ones are very, very reactive, right? Very reactive nonmetals, very reactive metals. Now, these ones are called halogens, while these ones are called noble gases. This is, of course, just a bit of revision. They are very, very stable. Okay. Let's keep going. So how would the results have been different? No explosion. There would have been no explosion because helium doesn't burn. No explosion because helium is stable. Helium doesn't burn. That's what would have been different. Right, let's move on. Okay. So why do elements bond with each other? Well, it turns out when elements bond with each other, they form these things called compounds. So compounds are new substances. It's a new substance that is made of two or more elements that are chemically bonded together, as opposed to mixed together, because that becomes a mixture. Okay, mixtures are not chemically bonded together. Mixtures can be separated quite easily. Compounds, on the other hand, are a bit more tedious to separate because compounds is two or more elements that are chemically bonded together, and that's slightly different. Now, what causes an element to bond with another element? Well, simply put, the reason is, drum roll, is electrons. Elements want to have complete outer shells. If they don't have complete outer shells, they will do everything in their power to have a complete outer shell. Look at magnesium over here. Magnesium has 2 electrons in the first shell, which is the complete number of electrons. That's the maximum, 2 in the first one. In the next one, it has 8, and that's also the maximum because it can only have 8 in the second shell. But what about the third shell? How many electrons does magnesium want there? It wants 8. It wants 8 electrons. Unfortunately, it only has 2. Now remember the secret number, 8. It wants 8, but it has 2. Now what's easier for magnesium? Get rid of 2 or gain 6? Because remember, it wants 8, one way or another. If it gets rid of 2, it will have 8 on the outside because then it will just be the second shell. If it gains 6, it will have 8 on the outside. But it's definitely a lot easier for magnesium to get rid of 2 than to gain 6. And so that's what magnesium is going to do. It's going to get rid of 2. How is it going to get rid of 2? Well, it's going to find elements that want the 2. So for example, magnesium has 2 electrons, right? It has 2 valence electrons. How do we know that? It's in group 2. Remember, everything in group 2 has 2 valence electrons. And just to remind you, valence electrons are the electrons on the outside that are in charge of reactions. So when reactions happen, they happen because of valence electrons that are on the outside. So magnesium has 2 valence electrons. Now, what is it going to do? It's going to go and find someone. Let's say fluorine. It's going to go and find fluorine, and fluorine is missing an electron in the outside. How do I know fluorine is missing an electron? Well, fluorine is in group 7 or 17. So that means it needs 1 to have 8. Remember, it's in group 7, so what does that mean? It's got 2 on the inside, 8 on the outside, that's 9, plus another 7 on the outside, so it's missing 1. All of the halogens, everything in this group, everything in the halogen group is missing 1 electron. It needs 1 electron so bad. Now magnesium wants to give away 2 electrons. Magnesium is like, yeah, sure. Hey, you want an electron, fluorine. I have 2 electrons. I want to get rid of them. So here's 1, but then I have another one. How about you go and get yourself another friend, get another fluorine. And so fluorine will bring another friend over, and then we'll have a happy family. Magnesium will get rid of its 2 electrons, and fluorine will take 1 each, but we'll have 2 fluorines, and then we'll have a compound, a very happy, stable compound called magnesium fluoride, which in chemistry we call a salt. That's exactly how it happens. This is called an ionic compound. One of them gives, the other one takes. Magnesium gives 2 electrons. Fluorine is happy to take the electrons. But fluorine just wants 1, so it needs 2 fluorines. Okay, let's do another example real quick. Now we're going to visit this in the next video, so I'm not going to spend too much time on it, but I'm just going to do another example. Let's say lithium. Lithium is in group 1. As you can see, it's in group 1, so that means it has 1 valence electrons. In fact, the dot diagram for lithium looks like this, because dot diagrams show us the valence electrons. So lithium has 1 dot on the outside. Now what about chlorine? Let's look at chlorine. Chlorine is in group 7. And chlorine has 1, 2, 3, 4, 5, 6, 7. What are you noticing? Lithium is missing 7. So it's much easier for lithium to just get rid of the 1. And chlorine is missing 1. So it's much easier for it to get the 1. So what's going to happen is this guy is going to meet this girl, and they're going to get married. He's going to say, you know what, I'll give you the electron, you'll be happy, and I'll be happy. And this is what happens. We get another salt, another compound called lithium chloride, which is very, very stable and extremely happy. So it's all about electrons. Compounds, new substances that don't have the properties of the elements, the original elements that formed them. I'll give you a quick breakdown. Lithium. Lithium is a metal. It's in group 1. It's a reactive metal. You put it in water, it'll start sparking. It'll fizz, it'll spark, it'll make bubbles, it'll smoke up. Lithium is reactive. Chlorine, another reactive element. Chlorine is a nonmetal. It's a gas. It's green in color. They used to use it in World War II. It's completely lethal. Okay, it's so reactive, it's lethal. If you breathe in some chlorine, pure chlorine gas, let's just say it's not going to end well for you. So then what happens when lithium meets chlorine is we get this beautiful white salt, solid white salt called lithium chloride. And it's completely safe. It's completely safe. Yes, like sodium chloride, which you eat. It's fine. You know why? Because it's stable. There's no electrons getting lost. There's no electrons getting gained. It's all about electrons. Okay? Now you know it's all about electrons. Right. So that's what happens there. So what's the whole business with, we know valence electrons are electrons on the outside. What is this whole business with dot diagrams? Dot diagrams is just an easy way to show how many valence electrons something has. So if you look at the groups here, the groups represent the valence electrons. I don't want you to look at transition metals. Those are an exception. So we won't look at that just yet. Those are transition metals. Transition metals, when it comes to oxidation states, they have multiple oxidation states. They form colored compounds. They're very interesting, but they're not part of this rule. So let's look at group 1. Group 1 has 1 valence electron because it's in group 1. So everything in group 1 is drawn like this. Hydrogen, 1 dot. Lithium, 1 dot. Now, where do I put the dot? It doesn't matter. It doesn't matter. Potassium, 1 dot. Why is potassium with a K? Because it's Latin. Okay? So some of these elements, they're English, and some of them are Latin. So hence why they have different spelling. It's not the English spelling. So potassium with a K. Then we've got rubidium, which is also 1 dot. Why? It's in group 1. Okay, let me see if I understood this right then. So everything in group 2 will have how many dots? 2 dots. Magnesium, 2 dots. Calcium, it's in group 2, 2 dots. That means it has 2 valence electrons. 2 electrons it wants to get rid of. Metals want to get rid of electrons. Non-metals want to gain electrons. So it's as simple as that, right? So then we have group 3. Let's do group 3. Aluminium. One of my favorite elements. It's readily available. It's used in window frames. And of course, it helps us fly. Airplanes are made of aluminium alloys. So aluminium, group 3. Aluminium. Very light, by the way. For a metal, it's very light. What's the deal with aluminium? Look at aluminium. It's not reactive. It's not highly reactive. Okay, because it's not in group 1 and 2. It's in group 3, so it's one of the lighter metals, and that's why we use it. It does form an oxidation layer, like an oxygen layer, because it reacts with the air, but it's safe. Aluminium is in group 3. How many dots does it have? Un, dos, tres. That's it. Right? That's it. Easy peasy lemon squeezy. Carbon, group 4. Un, dos, tres, quatre. I'm using French, by the way, to count today. Group 5, we've got nitrogen. What is it gonna be? 1, 2, 3, 4, 5. That's it. It's as simple as that. What about something from group 8? Let's do argon, which is a gas, a noble gas. 1, 2, 3, 4, 5, 6, 7, 8. Simple as that. Simple as that. Now you know it. Let's keep going. Number of electrons in a neutral atom is equal to the number of atomic number. Of course. Why? The atomic number is the number of protons. The atomic number is the number of protons, which is positive subatomic particles. I have 3 of them here. How many electrons do I have? Well, it's neutral. That means it doesn't have a charge. So therefore, I have to have 3 negative ones. 3 negative to balance the 3 positive. That's how it works. That's how it works, boys. Just simple as that. What about here? Here I've got the mass number. That's the number of protons and neutrons. And remember, I said that's the average of the isotopes. So it doesn't have decimals in real life. So let's say 7. 7 minus 3, you have 4 neutrons, 3 protons, and 3 electrons. Yep. Okay. The electrons of the atom are found in different energy levels. The first one, energy levels are also known as shells, known as orbits, whatever you, rings, okay? So it's all the same. The first one has 2. The first one has 2. The next one has 8. 1, 2, 3, 4, 5, 6, 7, 8. That's the maximum. Now, it doesn't necessarily have 8, like lithium doesn't have 8. Lithium has 2 and 1. But then the maximum it could have in the second shell is 8. Okay, so it's 2, 8, 8. That's the way it goes. Let's keep going. Valence electrons, we've already covered those. Those are the electrons on the outside. They're involved in chemical bonding. They're involved in chemical reactions. The number of valence electrons also helps determine the chemical properties of the elements. Yes, of course. If we have 1 valence electrons, what does that mean? It means the element is trying super hard to get rid of it. It doesn't want it. It's so close to having a complete outer shell, it wants to get rid of it at any cost. It's super reactive. What do we call those elements? We call them alkali metals, group 1 in the periodic table. These guys here, alkali metals. They are super reactive because they have 1 valence electron, and they really want to get rid of it. Because they're so close to having a complete shell, they just want to get rid of it. These guys here are also close. They have 2 valence electrons. So they're also reactive. They want to get rid of the 2. They're not as reactive as those guys. They're not as pissed off. But they still want to get rid of those 2. So they're reactive as well. Now what about those guys here? 3. Less reactive still. 4. When you've got 4, that's a funny situation. You've got 4 valence electrons. So it's a bit like, well, I can take 4 or I can get rid of 4. I could do both. I could do both. So in that instance, you don't have reactivity per se, or you don't have high reactivity. Then what happens? Then a situation kind of flips over. You've got 5 here, so it's easier to gain 3. So now nitrogen, although not so reactive as a stable molecule, still would like to get 3. If it could get its hand on 3 electrons, it'd be happy. Oxygen, now we're getting a bit more reactive. Oxygen wants 2 to complete its outer shell. Fluorine, oof, that is very reactive because it's missing 1. It's like having Pokemon cards and then like missing 1 card from a complete set. Like it's just missing 1 electron to have a complete outer shell. So it's very reactive. But then what happens here is something very interesting. Group 8, noble gases. I wonder why they're called that. Why are they called noble? Because they don't need anyone. They have complete outer shells. They're happy. They don't need to give up any electrons. They don't need to gain any electrons, which makes them stable. They don't react with anything. You can breathe in helium and you can breathe it right out and nothing happens to you. You can't do that to chlorine. You can't do that to fluorine, I tell you what. But you can do it to helium. All right? Not that you should. Don't do it. Change your voice and all of that, but please don't do it. It's not a good idea to do that. So these are gases and they are very stable, noble gases. Okay, let's move on. We talked about valence electrons, group 1 elements. Of course, we've got hydrogen, lithium, and sodium. And what do you notice? They all have 1 on the outside. 1, 1, 1. They all have 1 on the outside because they're in group 1. Group 1, 1 on the outside. Group 2, 2 on the outside, and so on. As you go down the group, valence electrons are the same. Group 1 all have 1 valence electron. You know, we just figured that out. So everything in group 1 has 1 valence electrons. Okay, what about these guys here? Let's have a look. How many valence electrons does rubidium have? We've already explained that one. Rubidium has 1 because it's in group 1. So this is what it looks like. That's the dot diagram. Magnesium has 2 because it's in group 2. What about aluminium? Group 3, 1, 2, 3. You can also do it like that. That's fine. What about nitrogen? Group 5, 1, 2, 3, 4, 5. Bromine, that is group 7 or 17. So fluorine, chlorine, bromine, iodine, all of them have 7. They are halogens, very reactive nonmetals. And then neon has 1, 2, 3, 4, 5, 6, 7, 8. It is stable. It is happy. It does not need anyone. There you go. And here's some dot diagrams for hydrogen, carbon, and oxygen. Oxygen is in group 6. 1, 2, 3, 4, 5, 6. Why did they draw it this way? It's okay. You can draw it that way. Carbon, they drew it this way. Now, here's the thing. Now, can I draw carbon like this? Yeah, kind of, yes. However, electrons. What charge do electrons have? Negative. If I've got 4 electrons and they're negatively charged, now remember from grade 2, negative and negative repel each other, like magnets. Positive and positive repel each other. So since they repel each other, it's a good idea to draw them this way so that because they're kind of like going to just spread themselves apart from each other. So that's how we draw them. Okay, let's have a look at these examples over here. Sodium, number of valence electrons of sodium. Well, what do I need in order to solve this is I need my trusty, handy dandy periodic table. Okay, sodium is group 1 of the periodic table. So 1 valence electrons. And it's going to look like that. Okay. Aluminium, group 3. And it'll look like that. 1, 2, 3. What I'd like you to do is I'd like you to pause the video, do it yourself, and then unpause the video. Neon is in group 8. It's a noble gas. Magnesium is in group 2, and it has 2. Iodine is in group 7. Oops. So it has 7. And it looks like that. 1, 2, 3, 4, 5, 6, 7. Phosphorus is in group 5, I believe. And it has 1, 2, 3, 4, 5. Interesting. I used to teach chemistry. Loved it. Right, let's have a go. Which group has the greatest number of valence electrons? Of course, that's going to be group 18. Why? It's got 8. It's got 8 valence electrons. How many valence electrons are found in atoms of group 14? 4. Group 14 immediately. Just get rid of the 10 transition metal groups. It is group 4. It's 4. All atoms are most stable with or would prefer how many electrons in the valence shells? Most of the time it's 8. Most of the time it's 8. Sometimes it's 2, like helium and hydrogen. Sometimes it's 2n squared. So sometimes it's 18. But we'll not talk about those situations. What groups are the most reactive metals? 1 and 2. Because that's the alkaline metals and the alkaline earth metals. What groups are the most reactive nonmetals? 16 and 17. Why not 18? 18 is noble gases. They don't react. So the oxygen group and the halogens. How many valence electrons are in phosphorus? 5, because it's in group 5. Which group in the periodic table is most likely to gain an electron? Gain an electron? Of course, that's going to be a non-metal, because non-metals gain, metals give. Non-metals gain, metals give. So it's going to be group 17. That's the halogens. Once again, chlorine, fluorine, iodine, bromine, all of these guys. Okay, so now we get to reactivity. What is this business with reactivity? Reactivity, simply speaking, it's the ease and the speed at which an element combines or reacts with other substances. That's what reactivity is. So things that really want to get rid of their electrons are reactive. And things that really, really want an electron are reactive. That's it. That's what reactivity is. Okay? So noble gases, they're not reactive because they don't need anyone. They're fine. They're like at peace. They found their zen. Okay? They're completely at peace. So that's what we mean by reactivity. Let's talk about properties of metals and nonmetals. And this should be revision for the most part. Here's the metals. Metals are on this side of the periodic table and they're in green. Some physical properties of metals. Now, hopefully a lot of this should be revision. Most metals have these properties with few objections. There's always an objection, isn't there? The physical properties include malleability, or malleable, means it can be hammered into shape. That's what malleable means. It can be hammered into shape. Let's have a look. Can metals be hammered into shape? Is this true? Let's have a look. Now, here's a metal. I have a metal with me right now. That's a bracket. You see that? An L bracket. Let me make my face bigger. Okay. Now, look what happens. I can bend it. That's cool. Why can I do that? How can I do that? Well, it's a metal. Metals are malleable. That's what we mean by malleable. So that's pretty cool. Metals are malleable. Let me put my face back in the corner. Let's see. Can I place it in the corner where I was? Yeah, good enough. Okay, so metals are malleable. They are ductile. Ductile means they can be drawn into wires. Wires. Wires are made of metal. They have metals on the inside. So wires, they can be drawn into wires. And here's a good one here. Look, metal wires. Isn't that cool? Okay, so metals are ductile and malleable. They can be drawn into wires. Metals have luster. What does luster mean? They have a shine, a special shine. I wonder what this is. How do you know it's metallic? It's shiny. Shiny. What about this? Metallic. How do you know? Shiny. How about this? Oh, it's also shiny. Look, it's a Kenyan shilling. Ooh. It's got a giraffe on it. Isn't that cool? So all of these are shiny, and just like jewelry, they're shiny, so that means they're metallic and they are malleable and they're ductile. And of course, metals conduct heat and they conduct electricity. If we couldn't conduct heat and electricity, we would not have all the electronics we have today, and we could not cook because, of course, all our cooking utensils, or most of them, are made of metal, so that they can transfer the heat from the fire to the food. We've already explained that. So malleable means they can be hammered into shapes. They can be made into different shapes. Gold is one of the most malleable elements as well. It can be made into thin sheets. That's why in fancy restaurants, they make it into thin sheets and they cut it up and they sprinkle it over your food. Yes, they really do that, apparently, in some restaurants. However, I gotta be careful what I say here. Nothing happens to the gold, as in your body doesn't react with it. Why? Because gold is unreactive. It's not reactive. Like copper, like silver, it's really highly unreactive. So it comes in and then it just goes out. Yep. Anyway, so that's gold for you. Aluminium is, aluminium, of course, is very, very versatile. I told you it's one of my favorite metals. It can be made into aluminium foil. It can be made into these, what are they, containers and window frames, airplanes. Aluminium is amazing. Metals can also be drawn into wires. Of course, this tungsten wire over here, the one inside the bulb, that's made of metal. Luster, they have shine, shiny, 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 shiny. There's a whole industry. Jewelry is all built around metals being shiny. Thermal conductivity, they conduct heat, which is why we're able to cook. And of course, they also conduct electricity. Let's answer these questions real quick. Can be drawn into wires. What is that? That is ductile. Goes from solid to a liquid under high temperatures. Ooh, yes, that's the other thing as well. Metals have high melting points, very high melting points. However, there is one exception to this rule. Two, maybe a few more. The exception to the rule is mercury. It's liquid at room temperature. It's a transition metal, but it's liquid at room temperature. So this is mercury over here. Where is it? It's a transition metal, and it is liquid at room temperature. Here it is, mercury. The other kind of exception is gallium. Even though it's a metal, it's kind of almost liquid at room temperature. If you hold it in your hand and your hand is a bit warm, it'll melt in your hand. Able to be hammered into shape, but generally speaking, metals have high melting points. That means they don't melt very easily. Able to be hammered into shape, we've already explained that one. That one is malleable, able to be hammered into shape. Firm and resistant to pressure, hard. And reflects light, shiny, also known as luster. Chemical properties of metals. Two properties that I want you to know about. Metals give electrons or donate, that's the proper word, in a reaction. So when they're forming a bond, or when they're forming a compound, they give electrons, they don't gain electrons. Non-metals gain electrons. The next one is metals form oxide layers. React with oxygen to form oxide layer. So what does that mean? You know how iron, if you leave it for a while, what happens to iron when you leave it for a while? Let's see if I can find something that will explain what I'm trying to say. So after a while of leaving iron lying around, it becomes, okay, somehow I can't find an example suddenly. Well, that'll do. Here's a metal. What happened to it? It's rusted. How did it rust? It reacted with the oxygen in the air. Here's another one. This one's got a protective layer on it, so it didn't rust. Metals rust. Well, not all of them rust, but they form an oxide layer. Even aluminium does it. Lithium does it really well, because of course everything in group 1, they form oxide layers. These are called chemical properties. Metals give up electrons and metals form oxide layers. They react with the air. Sometimes they take longer, sometimes they take not so long. Iron reacts quite quickly and becomes rusty rather quick. So you have to protect the iron by painting it, or by oiling it, or preventing it from being open to oxygen, or maybe even mixing it with another metal or carbon to form stainless steel. You got to do something to protect it, or even sacrificial reaction by putting something else next to it so that it can react and help it not react. There's many ways, okay? But the point is, metals will react with oxygen. What about gold? Gold, I just said that gold is not very reactive. Even gold will form an oxide layer after a while, which is why you will need to go and get it cleaned, get your jewelry cleaned professionally after a while, because they form an oxide layer and it loses its luster, loses its shine. Boys, I will see you on the next one. I'm going to stop right there for now, and we'll continue this in part 2, inshallah. Take care. Bye-bye. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome back to another exciting session, and now we're talking about part two of lesson 3, where we're talking about metals and non-metals. So we've already talked about metals and how they are shiny, lustrous. They are sonorous. They conduct electricity and heat. They are malleable. Metals give up electrons and they form oxide layers. So those are some of the physical and chemical properties of the metals. Today we're talking about nonmetals and metalloids, and we're going to do a quick revision of lesson 2 as well at the end of it. So let's go. Without further ado, let's go. Nonmetals, as we've said, they are on the other side of the periodic table. Let me just do something real quick and see if I can do this. Oh, can't do that. Let me just open it. So this is where nonmetals are. As you can see in green, those are the nonmetals, and they are, okay, mostly gaseous, with the exception of a few that are liquid, like bromine, but mostly they are gaseous. Nonmetals do not have the same properties as metals. So by definition, if a metal conducts electricity, then nonmetals do not conduct electricity. If a metal is sonorous, then nonmetals are not sonorous. So that means they don't make a ringing noise when you drop them. So I'll give you an example of that real quick right now. I'm going to drop an item and you're going to tell me whether it's metallic or not. I hope you could hear that. So I think that's pretty obvious that that was metallic. Now I'm going to drop another item and let's see the difference. Let's try and listen to the difference now. Okay, I think most of you can tell that's a pencil. So obviously metals have that distinctive ringing noise. Let's do that again. Let's see if that works. That distinctive ringing noise. We call that sonorous. Right. So that's metals for you. Metals are sonorous. They are conductive of heat and electricity and so on. Non-metals are not sonorous. They are brittle. They're not as hard as metals. They're not malleable. And they do not conduct heat and electricity very well, I'm afraid. Right, let's move on. We're going to cover this in a bit more detail. So as we said, this is where the nonmetals are compared to where the metals are over here. Properties of charcoal. So charcoal is an example of a nonmetal. It's carbon. Charcoal is, as we said, brittle. It is not malleable. It doesn't conduct electricity and heat very well. Now some of you might be thinking, well, hang on, charcoal. We use that for burning. We do. It burns, but it does not itself conduct heat. In fact, I could probably use charcoal to make a handle for my frying pan. You know how frying pans, they have handles made out of plastic or wood. They can also be made out of charcoal, technically speaking. It does not conduct heat very well, but it self-burns, like wood. Wood does not conduct heat very well, but it burns itself. So that's what we're talking about here. Charcoal burns very, very well, but it does not conduct heat very well. Right, let's keep going. Physical properties of nonmetals. So we've already talked about the physical properties of metals. Malleable, which means they can be hammered into shape. They are ductile. Those are metals. They can be drawn into wires. Guess what it is for nonmetals? It's the opposite. So nonmetals are not malleable. They are brittle. They are not ductile. They cannot be drawn into wires. They are poor conductors of heat and electricity. They are dull and brittle. They have lower density. Ooh, I need to talk about that one. What is density? Density is how far away the particles are. So remember how everything is made of atoms, and atoms are like these little tiny particles. And how close they are together is what determines density. So if things are very, very close together, then they are dense. And solids, generally speaking, are more dense than liquids, which are more dense than gases. Well, liquids and solids, they kind of have the same density, but we don't like to talk about that. Because liquids are not compressible either. But anyway, different materials have different densities. And so in physics, for example, the definition of density is mass over volume. Okay? So if something has a mass of 1 kilogram, but it takes up a volume of this much, then it's going to be very dense. It's going to feel very heavy. But if it's got a mass of 1 kilogram and it takes up a density of, a volume of this much, then it's going to be rather light, or it's going to feel rather light. And there's an old joke about this, like what's heavier, a kilogram of feathers or a kilogram of iron? And we all know it's the same. It's 1 kilogram. It's the same weight, but the density of the feathers is way less than the density of the iron, right? And that's what we're talking about. When it comes to density, it's how far away the particles are. Non-metals, the particles are very far apart, okay? And so that's why most of them are gaseous, with the exception of bromine. Whereas metals, they're very dense. Metals are heavy. Metals feel heavy. If I just show you something right now, I think you're going to get a feeling. And that feeling, that's because metals give us that feeling. That, can you feel it? Can you feel how heavy that is? I think you can. I think you can. Like, you can generally almost feel it. Okay? That is a metal, right? Metals are dense. They feel heavy. Right, let's keep going. Let's see if I can show you something else. How about this? See, that's fluffy. That's not so dense because the particles are far apart. I don't have anything else. I do have a hamster, but I'm not sure where he is. He's run away. Right. So, many nonmetals are gases at room temperature. Bromine is the only nonmetal that is liquid at room temperature. Okay, let's keep going. So, chemical properties of nonmetals. Now, remember we talked about how metals give up electrons, because metals, group 1, group 2, group 3, they like to give up electrons. Now, why is that? Because it's easier to make a complete outer shell. It's way easier. If you have 1 or even 2 or even 3 electrons, it's easier to give up those than to gain 5, 6, or 7 electrons to have a complete shell. What about nonmetals? Let's look. So let's take a nonmetal in group 7. I want you to think about this carefully. So here it is. It's in group 7. So that means it has 7 electrons on the outside. So here's fluorine, and fluorine has 1, 2, 3, 4, 5, 6, 7 electrons on the outside. I don't like that last one, so I'm going to fix that. Here we go. So fluorine has 7. Now, what do you think? Is it easier for fluorine to lose the 7, or is it easier to gain the 1? Of course, it's easier to gain the 1. And so, you just answered the question. Is it easier for nonmetals to gain electrons or lose electrons? Nonmetals, it's easier to gain electrons. Okay? Metals, easier to lose electrons. In fact, we call them electron donors. Okay? If you guys are interested. Electron donors. Metals are electron donors. They donate electrons. Whereas nonmetals are electron, come on, try and give it a go, electron acceptors, right? So nonmetals accept electrons, so we call them electron acceptors or electron takers if you want to. Nonmetals, metals on the other hand, are electron donors or electron givers, okay? I hope that makes sense. So one of the chemical properties of nonmetals is that they accept electrons. Nonmetals also react with metals and other nonmetals. They do this by sharing electrons to form a compound. So yes, so metals don't react with other metals. Metals, you can mix metals together. For example, you can mix like copper and tin and chrome and brass and so on. That's actually how you make brass and other alloys like stainless steel and stuff. Stainless steel is iron and carbon in certain percentages, like 0.5% carbon and 99.5% iron, and a bit of chrome can give you stainless steel. Now, these are called alloys. They're mixtures. Whereas nonmetals, here's something else about nonmetals. Nonmetals can actually bond and form compounds with other nonmetals. So example, carbon and oxygen. Carbon and oxygen make carbon dioxide. Hydrogen and oxygen make water. Okay? Sulfur and oxygen make sulfur dioxide. So all of these are nonmetals. Nonmetals can actually form compounds with other nonmetals, and they do that by sharing electrons. And we're going to learn about sharing electrons in covalent bonding a bit later on. Metal or nonmetal? What do we think? This is chlorine gas. I can tell because it's green in color and it's gaseous. And chlorine gas, of course, is a nonmetal at room temperature. What about this guy here? This is a powder. And it's a nonmetal powder. I know what it is. It is phosphorus. Phosphorus is a dull powder. It's a poor conductor of heat and electricity. It is a nonmetal. I don't know what this is, but I know it's metallic. And it's a bit on the brittle side, so it could be a hard metal. Tungsten, titanium. Titanium has a high luster and a strong and hard metal element. It is a metal, yes. Metal, non-metal. I can tell it's a non-metal because it doesn't look metallic. Yellowy non-metal. No. Sulfur? It is sulfur. Sulfur is brittle, dull element that is poor conductor of heat and electricity. Anyway, so then we come to something called metalloids. Metalloids are these guys over here. They are the ones in yellow. Metalloids are very interesting because they actually have been really useful lately. Why is that? Because we use them in electronic circuits. You know what? Electronic circuits, we use a lot of this guy, silicon. Okay? So, and they're semiconductors. So what does semiconductors mean? Means they kind of conduct electricity. Well, not kind of. Like if you pass electrical current through them, then you can make them more conductive. And if you don't, then you make them less conductive. And that's useful. So you can actually control how conductive they are. And that is what we use for transformers and for gates inside digital and analog circuits. And that's why we use them. So semiconductors are used in electrical circuits. And they can be used to control currents. So we've got things like germanium. We've got things like silicon, obviously silicon chips, and transistors. That's the word we're looking for. Not transformers, transistors. So they're used in electronic circuits, electric circuits. Okay, so that's what metalloids are used for. That's as far as you need to know for now. They're very, very interesting. Metalloids, they separate metals from non-metals, as you can see over here. They separate metals from non-metals. Those are metals, and those are non-metals. So they separate the two. Metalloids have some of the properties of metals and some of the properties of non-metals. They are all solid at room temperature. However, gallium, where's gallium? Over here. Oh, I suppose it's a metal. It's got a low melting point. Anyway, so they are all solid at room temperature. They are brittle, hard, and somewhat reactive. And some metalloids are semiconductors. That means they can conduct electricity under some conditions, but not under others. So if you pass heat through them, they become a bit more conductive. If they pass electricity through them, they become... So it depends on what the conditions are. Okay, let's look at the lesson check. Use figure 4 of this lesson to help determine the number of valence electrons in atoms of each of the following. So I've got something similar here. Chlorine. Chlorine is over here. It's in group 7, so it therefore has 7. Calcium is in group 2, so it's got 2. It's very hard to write on this. Cesium in group 1, so it has 1. Neon is in group 8, so it has 8. Tin, well, that's a bit of a tricky one. It's in group 4, so it has 4. Okay, and then because that's tin over here. Okay, so it's in group 4. Indium, that's in group 3, isn't it? Indium, yes it is, it's right here. And so it has 3. Draw an electron dot diagram for each element in question 1. So I'm not, yeah, sure. I'll do a few. Chlorine, 1, 2, 3, 4, 5, 6, 7. That's basically it. Easy as that. Calcium, 1, 2. I can also do it this way. But remember what I said earlier. Electrons are negatively charged, so they like to be far away from each other. Let's do neon. And neon is a noble gas. So it has a complete full outer shell, and that's kind of what it looks like. 8. Okay, and indium, we'll do indium. 1, 2, 3. Or we can do that as well. 1, 2, 3. Okay. Underline each statement. This is now doing number 3 now. Underline each statement that is true about the element sulfur. Use figure 4 to help you. Sulfur. What is it, first of all? Where is sulfur? It's over here. So we know it's a non-metal. So properties of non-metals, guys. Properties of non-metals. Is it a metal? No. Each of its atoms has 16 electrons. No. Oh, yes, it is, because it is number 16. I'm going to underline this one because it says underline, doesn't say tick. It has a dull appearance. It sure does because it's a nonmetal, and nonmetals by definition have a dull appearance. Conducts electricity? No. Each of its atoms have 5 valence electrons? No, they have 6 valence electrons. Don't they? Yeah, because it's in group 6. Its electron dot diagram has 6 dots. Yes. Yes, it does. So this is what it will look like. 1, 2, 3, 4, 5, 6. Because it is in group 6. Right, let's look at number 4. Hydrogen is a nonmetal with many nonmetal properties. Why is it on the periodic table with metals in group 1? Okay, so hydrogen is a special case. Hydrogen is a nonmetal, but hydrogen is also reactive, so it has similar properties to all these guys over here. Now remember what we said. Elements in the same group have similar properties. Elements in the same group have similar properties. Elements in the same group have similar properties. So hydrogen has similar properties to lithium, sodium, potassium, all of it. It's very reactive. It also has 1 valence electrons. Everything in here has 1 valence electrons. So two main reasons, is that it is very reactive, so it shares some of those physical properties or that group 1 does. And the other reason is because it has 1 valence electron. So it has 1 valence electron as well. And so its chemical properties as well kind of match those of metals. Is that sometimes it's easier for it to get rid of the electron. Although there are many cases where it gains an electron. And there are many cases where it shares an electron, as in the case with water. So it's a very interesting scenario. It's also been called a proton. Hydrogen is the most common element in the universe. Okay, it's a very interesting one. So anyway, why is it in group 1? It has 1 valence electron. It shares chemical and physical properties. It shares chemical properties with metals. It shares physical properties with nonmetals. It's also reactive, like similar to group 1 elements. Right, let's keep going. Oh, where are we? Oh, so we've got a mind map here. And feel free to pause this or print it out. I think it's an excellent mind map. This is courtesy of a colleague of mine. And I just thought it was wonderful. I thought I'd use it. So metals, they are the left side of the periodic table. Most elements are metals. And the chemical properties of metals easily react with other substances. Well, yes, so metals lose electrons. They have 1, 3 valence electrons. If they are in group 1, they have 1. If they're in group 2, they have 2. If they're in group 3, they have 3. And they're made of crystalline solids. So what that simply means is they are solids and they are structured. Physical properties of metals. They are malleable. They can be hammered into shapes. They are ductile. They can be pulled into wires. They have thermal conductivity. They can transfer heat. They are solid, okay, except for mercury. And gallium has a low melting point, but it's still a solid. They are lustrous, so they're shiny and reflective. And they are conductive of electricity. They can carry electric current. True or false? Let's do some quick revision of this lesson. Metals are generally good conductors of electricity. Of course, that is true. Please pause these, do them yourself before you reveal the answer. Nonmetals tend to gain electrons when forming chemical bonds with other elements. Nonmetals tend to gain electrons. Let's see, where are nonmetals? Over here. So, of course, in order to form complete outer shells, with the exception of noble gases, they don't bother with anyone. But these ones here, in order to form complete outer shells, they gain electrons. It's easier to gain 3, 4, or 5 electrons. 3, 2, or 1 electrons. What about carbon? You know, somebody might ask me, what about carbon? Carbon's group 4. It has 4 electrons. Would it be easier to lose 4 or gain 4? Well, carbon actually does both. It can gain and it can lose electrons. It's a very interesting scenario. And if we're being really accurate here, it doesn't actually like lose or gain electrons per se. It shares electrons. So that's what carbon likes to do because it's in group 4. So it's like, oh, should I share? Should I lose or gain electrons? Technically speaking, it actually just shares electrons instead. Right, let's keep going. So nonmetals, of course, tend to gain electrons. Sodium is a nonmetal because it is highly reactive and does not conduct electricity. That is false. On quite a few... Here's the thing. Is it highly reactive? Yes. But being highly reactive does not make you a metal. Because fluorine is highly reactive. Okay, so here we go. If we look over here, fluorine is highly reactive, chlorine is highly reactive, and these are nonmetals. So being highly reactive does not make you a metal. And of course, that other statement is fully wrong. Does not conduct electricity. That's also wrong. So this is false. Of course, just to go back to sodium. Sodium is in group 1, and everything in group 1 conducts electricity because they're metals. They're soft. You can cut them with a knife, actually. You can cut them with a plastic knife. That's how soft they are. And they float on top of water. So even though metals have high density, these ones here have lower density. But they are very reactive and very soft, but highly reactive. One of the defining characteristics of metals is that they are malleable and can be easily hammered into thin sheets. Yes, they are. Metalloids. Metalloids are what? Let's see, just a second, sorry. Are often used in semiconductors, or semiconductors, which are important components in electronic devices. Yes, of course they are. Okay, and let's come to a quick revision. So this is a quick revision of lesson 2. Okay, it's a quick revision of lesson 2, which I think is quite important. How is the periodic table organized? So hopefully by now you should know that the periodic table is organized by atomic number or number of protons, because that is the ID, that is the identity of the atom. Okay, so I think it's a good idea if you print this out and you actually write the answers in here. So it is organized by atomic number. That's how the periodic table is organized, by atomic number. By atomic number, or the number of protons. What can you tell me about the element from its location in the periodic table? So let's see. What can you tell me about sodium? Which group is it in? It's in group 1. It's highly reactive. So you can tell me a lot about the element from its location. You can predict a lot. What if I tell you, for example, tell me about xenon? And you're like, well, I don't know much about xenon. I tell you, well, it's a noble gas. It's in group 8. Then you can tell me, oh, it's one of those elements that don't need any other element. It's sufficient. It's got a complete outer shell. So you can tell me a lot about an element from its location. You can tell me about its properties. All right? Let's try another one. What about magnesium? So you can tell me, oh, magnesium is a little bit reactive as well because it's in group 2, and those are reactive as well. So those are alkaline earth metals, and they're quite reactive as well. Right. Let's have a look. So we've done 1 and 2. What can you say about group 1? So group 1 is a group of elements that all share similar properties, because of course we put the elements that share similar properties together. So group 1 all share similar properties. They are highly reactive. They have lower density. They can be cut with a knife. You can cut them with a knife, literally. I showed you that video in class. And they tend to share similar properties, so they actually become more reactive the lower you go down. So cesium and francium are extremely reactive and explosive when they react with water. And of course, as far as chemical properties are concerned, they donate 1 electron. They have 1 valence electron on the outside, and they are happy to give up that valence electron. Which group is the second most reactive group of metals? Well, we've already answered that one as well. So it is group 2, also known as alkaline earth metals. Alkaline earth metals. And these ones are called alkali metals. So we've got alkali metals and alkaline earth metals. Alkali metals are by far the most reactive metals. Alkaline earth metals are the second most reactive metals. And the most reactive nonmetals are the halogens. These are the noble gases. Noble gases. Okay. This is the oxygen group, nitrogen group, carbon group, bromine group. What can you say about the elements in the same group? We've already answered that one as well. Elements in the same group have similar properties. So everything in here has similar properties. The halogens. Why is that? Because they all want that electron. Okay? They're all reactive. Everything in here has similar properties. They're all very satisfied. They all have complete outer shells. Everything in here is highly reactive. And so elements in the same group share similar properties. What are transition metals? Let's answer that one. Transition metals are these guys over here. They are the transition between 1 and 2 and 3, 4, 5, 6, 7, 8. So transition metals are this group over here. They are conductive. They have more than one oxidation state. Which means they can lose more than one electron. So they can lose 1, 2, or 3 electrons at a time. They form colored compounds, which are very interesting. Transition metals tend to be quite useful in electronics as well, as some of them are superconductors. So things like silver and gold are superconductors. Copper, of course, is used widely in electrical wires as well because it's highly conductive. So these ones here are transition metals. Okay, an example is titanium, an example is chromium, manganese, iron, cobalt, nickel, copper, zinc, vanadium. All of these are examples of transition metals. What can you say about halogens? So we've already talked about them. Halogens are the most reactive nonmetals. And they're mostly gaseous as well, except for bromine, which is liquid at room temperature, and they are highly reactive because they are missing one electron. What makes noble gases so special? They don't need anyone. They have complete outer shells. What is the difference between a period and a group? Well, simply speaking, that is a group, that's another group, that's another group, that's another group. What's a period? That's a period. That's another period. So this should be a revision. Hopefully you all know that. And with that, I would like to say best of luck. I will see you in the next one. Over and out. Adios. Ciao.